Today we'll talk about Fast Fourier Transform. What is it and why you need it? Let's solve easy problem. You have two integers, you want to calculate their product. So you have some integer a and some integer b. Let's say the length of this integer is n. So they both have n bits. And you want to calculate product a multiplied by b. What will be the time complexity if you just calculate the multiplication using some naive algorithm? So what you do when you multiply two integers, you take each digit of one integer, multiply it by another integer, and then take sum of all these products. Yeah. So you take each digit of b, multiply it by a, get some number, then calculate sum of these numbers. So you have n integers of size n. Then you calculate sum of these integers. You will calculate sum in linear time. So the total time complexity of multiplication, if you just do it like you usually multiply numbers, will be n squared. And the interesting question is if it is possible to calculate the product of two integers faster than n squared time. And answer is yes. Yes. So how to calculate product of two long integers faster than n squared time? Well, first of all, let's think not about integers but about polynomials, because it's slightly easier to calculate polynomials, not integers. So let's say you have two polynomials of size n. So you have polynomial a of x, something like let's say a0 plus a1x plus a2x squared plus and so on plus anx power n, and polynomial b, let's say of the same size. And you want to calculate the product of this polynomial. Let's c of x equal to a of x multiplied by b of x. So the product of two polynomials is a polynomial. Yeah. So I want to find the coefficients of this polynomial c. So this polynomial c is something like c0 plus c1x plus and so on plus c. So the degree of this polynomial will be 2n x power 2n. So how to find the coefficients of this polynomial? Any ideas? Say something. Okay, I just want to check that anyone is listening what I'm talking about. So how to calculate the coefficient or coefficient c of this polynomial? Go on, say something. Nice. Okay. Fine. Yes. Yes. We need to take sum of all possible products of two coefficients of a and b, such that the sum of the powers of x will be equal to I. So I need to, for example, if I want to calculate the first coefficient, will be just product of these two coefficients. Second coefficient will be sum of this pair and this pair, and so on. So each coefficient c is sum of all products a and let's say j and b I minus j. calculate coefficients of polynomial C, we need to calculate these sums. But again, if you just do it like usually, calculate this sum, and you have a quadratic algorithm. Yeah. So you need to calculate n coefficients. For each coefficient, you need to calculate the sum in linear time. Yeah. So total time complexity again will be n squared. So the idea is to calculate these sums faster than n squared time. Nice. Let's go. So the first algorithm I want to discuss is the Karatsuba algorithm. So how Karatsuba algorithm works? It works using some divide and conquer technique. So let's say you have polynomial A and B. Let's split each polynomial into two halves. So let's say polynomial A is sum of polynomial A1 plus, so let's take this lower coefficients in one polynomial and higher coefficients in another polynomial. So plus x in power n over 2, A2, something like that. So again, I'll take polynomial A. So these coefficients will be A1 and these coefficients will be A2. So here the powers of x are from 0 to n over 2 minus 1, and here powers are from n over 2 to n. And do the same for the second one. So for the second polynomial, I have b1 plus x power n over 2 b2. Now, what happens if I multiply these two? If I multiply these two things, I will have something like a1 b1 plus x in power n over 2 a1 b2 plus a2 b1 plus x power n a2 b2. Yeah. Here. Now, again, I use divide and conquer technique. Yeah? So now I want to calculate the product of two polynomials of degree n. So I split each polynomial in halves. And now I have 4 recursive calls. 1, 2, 3, 4 recursive calls. So each of these recursive calls is to calculate the product of two polynomials of degree n over 2. Yeah? So what I will have? So to calculate this product of two polynomials of degree n, I made something linear plus 2 recursive calls or 4 recursive calls plus 4 recursive calls for polynomials of degree n over 2. Now, if I have this recursive, what will be the time complexity? Again, how to calculate time complexity? You have 4 recursive calls. Each time you divide problem you divide the size of the problem by 2. Yeah. So the depth of your recursion will be logarithm base 2. Yeah. And the number of calls will be 4 in power logarithm base 2. Yeah. So it's 4 in power log base 2 of n. Yeah. And what's this? Once again, what's happening? I have problem size n. Yeah. I make 4 recursive calls. Each recursive call has size n over 2. Yeah. Now again, I'll have 4 recursive calls and so on. So the size of this recursion will be log base 2 of n. Yeah. And the number of recursive calls will be 4 in power of depth of recursion. Yeah. So 4 in power log base 2 is just n squared. So again, we found another algorithm of time complexity n squared. But what we can do, we can improve it. So let's see what's happening here. Here we don't need to have these two products separately. We need to calculate only sum of these two products. Yeah. So to calculate sum of these two products, we will do the following trick. We will have so instead of calculating these two products separately, we will calculate the product of A1 plus A2 multiplied by B1 plus B2. If we calculate this product, we will have something like A1 B1 plus A2 B1 plus A1 B2 plus A2 B2. Yeah. Now, from this product, we can subtract A1 B1 and A2 B2. And if we subtract this and this, we will have exactly the sum we need. So again, once again, we will make 3 recursive calls. 1, 2, and 3. From these 3 recursive calls, we will get this product, and sum of these 2 products. Because we will get these products, subtract A1 B1, subtract A2 B2, and get this sum. So instead of 4 recursive calls, we'll have only 3 recursive calls. Like this. And time complexity will be different. Time complexity now will be n in power log 3 base 2, like this. That's all. That's how we improve time complexity. So we have an algorithm which multiplies 2 polynomials of degree n in this time complexity. It's called Karatsuba algorithm. It's actually one of the first algorithms known for multiplication to polynomials faster than n squared time. Now we'll discuss fast Fourier transform. So fast Fourier transform is another algorithm for multiplication to polynomials, and it works even faster. Using fast Fourier transform, we can multiply 2 polynomials in almost n log n time. So our goal today will be to calculate product of 2 polynomials in n log n time. Almost. Let's go. So what is the idea behind fast Fourier transform algorithm for the multiplication of 2 polynomials? We will do the following. Sorry, I don't need this anymore. Let's write this. First of all, I have 3 polynomials and they have different degree. So these 2 polynomials have degree n, this polynomial has degree 2n. It's not very useful, so let's extend polynomials a and b to degree n, just add 0 coefficients in the end. So all 3 polynomials have the same degree and call this degree n, just for simplicity. So I have polynomial a0 plus a1x plus and so on plus an minus 1 x power n minus 1. So I want all my polynomials to have n coefficients. Yeah. So now b0 plus b1 x plus and so on plus bn minus 1 x power n minus 1. And product will be polynomial c. Okay, this n is different from this n. This n is basically 2n plus 1. So the maximal number of coefficients in polynomial c is 2n plus 1. So I will just redefine this n to be 2n plus 1. Just to have all coefficients have the same number of, just to have all polynomials have the same number of coefficients. Okay? Now all my polynomials have n coefficients. Now, what is the idea? The idea will be following. So let's pick some n values. So let's pick values x0, x1, and so on, xn minus 1. And now let's calculate the value of polynomials a and b in these endpoints. So I will calculate values let's say ui will be the value of polynomial a in point xi, and say vi will be value of polynomial b in point xi. So I will just pick some n values, some n coordinates, and calculate values of these two polynomials in these n coordinates. Now I need to calculate values of polynomial c. So I need to calculate values. Let's see, zi will be the value of polynomial c. Okay, this is step 1. This is step 2 in polynomial xi. Now, when I know the values of polynomial c in some n points, so my polynomial has n coefficients. So if you know the values of your polynomial in n points, you can reconstruct your polynomial using some Lagrange interpolation, something like that. So now, using these values, I can reconstruct the values of. So from c, I will reconstruct values of c. Like this. Yeah. That's the whole point. So again, 3 steps. First, I will calculate the values of my polynomials in n given points. Now, using these values, I will find the values of polynomial c in these points. Now, using the values of polynomial c, I will reconstruct the coefficients of this polynomial. Very simple. Okay, what is the easiest step from this 3? What do you think? I claim one of these steps is really simple. Which one do you think? First step is actually not that simple. So if you just try to calculate the value of polynomials in each point, you actually need to follow all the coefficients and calculate this sum. So you will calculate the value in linear time, and you have linear number of elements here. So if you just do it like you usually calculate the values, it will take n squared time. Yeah, the easiest step is actually step 2. Step 2 is really simple. So again, polynomial c is product of polynomials a and b. So to calculate value of polynomial c, you just multiply values of polynomial a and b. So in any point, value of polynomial c will be just value of polynomial a multiplied by value of polynomial b. And we know values of polynomial a and b. So it's just product of u and v. So this is really simple. Nice. Steps 1 and 3 are actually complicated, and that's where we need something like fast Fourier transform. So this is called this is basically called Fourier transformation. This is the inverse of Fourier transformation. Whew. Let's go. So to make the fast Fourier transformation, we need 2 things. First, let's split this. First, we want our n to be a power of 2. So I want number n to be 2 in power of 2. No, it's easy. So if n is not power of 2, we will just extend all the polynomials to the closest power of 2. The size of the polynomial will be increased at most twice, right? So that's how you usually get something in power of 2. So it's easy, yeah? So again, you have some polynomials. If the size of your polynomial is not power of 2, you will extend your polynomial with 0 coefficients. So you have a polynomial of size n, of size power of 2. Now, second thing is interesting. Now we need something what is called primal root of not primal root of 1. So we need some special number. This number must have the following properties. So I want w power n equal to 1. And I want all the powers of n will be from 0 to n minus 1 will be different. So if I take the power 0, the power 1, the power 2, and so on, w power n minus 1, they must be all different. How to get this number? So the problem is that in real numbers you don't have this number. So in real numbers, if n is greater than 2, right? So if n is greater than 2, then you have only roots of 1 minus 1. And if you have only 1 minus 1, then here we have only 2 values. So if n is greater than 2, root of unity, yeah, that's how it's called. Okay. Yes, I need root of 1 of degree n. So in real numbers we don't have this number. So we now have two possibilities. We can go to complex numbers, or we can go to let's say modular arithmetics and generators and stuff. So first, if you use complex number, how to find this number? So in complex number you can take let's say let phi e in power 2p divided by n, right? Like this. So it's basically like if n equal to 8, so it's this number, right? Again, if this is your w, then if you take the powers of this w, so here you will have w squared, here you will have w cubed, here you have w power 4, w power 5, w power 6, w power 7, and here you have w of 0 equals to w power 8. Yeah. So in complex number you can take this number as your base. And now the possibility is to work in some modular space. So you take all your calculations by some prime modular. So if you take prime modular p, let's see. How to find this number if you have prime model? So we discussed prime models a few lectures before. So basically, in prime model you have generator. Yeah. So you have generator power p minus 1 equals to 1. Yeah. So I have a generator. If I take the powers of this generator, I take all the numbers from 1 to p minus 1. Now I want a number such that this number w must have period n, and my generator has period p minus 1. So to have a number which has period n, first of all, I need this p minus 1 to be divisible by n. So it only works if p minus 1 is divisible by n. If it is divisible by n, then I can take g in power p minus 1 over n as my base. So you can take a prime modular, take its generator, and if p minus 1 is divisible by n, you can calculate your base like this. So interesting thing that is it's not working for any prime modular. So it's only working for prime modules. So we want this n to be a power of 2. Yeah. So this p must be something like 2 in power of k by some t. Yeah, plus 1. So I need not some prime modular, but the prime modular of this form. So I need the prime number such that p minus 1 is divisible by big power of 2. So again, 2 power of k is a power of 2, which is bigger than my initial size of polynomials. Yeah. So I want not any prime number, but the prime number which is divisible by some big power of 2. Fortunately, there are some prime numbers of this like this, so it's usually not a big problem. But again, fast Fourier transformation is not working for any prime modulo. It's working only for prime modulos like this. So let's imagine you have all these prerequisites. So you have n to the power of 2. You have number level like this. Now what? What now? What we'll do? So let's go back here. For this algorithm, we need to pick these numbers x, and we can pick any numbers here. So the idea is just to pick good numbers x. So we'll pick good coordinates here, such that for these good coordinates we can calculate these polynomials efficiently. What is variable c is just some number, it doesn't matter. It's just p minus 1 divided by n, some integer number. Okay, let's think mostly about complex numbers just. But if you can do the same trick in using prime models. I'll just write this to keep some space. So I'll think about complex numbers, but you can do the same with prime models if you have a good prime model. Now, what numbers I will pick as my numbers x? I will pick just the powers of w. So I will pick xi is w in power I. So these 8 numbers will be the numbers I will use here to calculate these values. What's interesting about these numbers? Interesting about these numbers is basically when they are close to so when I calculate these polynomials, I need to calculate these x's in some powers. And if you calculate these numbers, if you calculate powers of these numbers, they will still be in this set. So all the powers of these numbers will be in the same set of numbers. So that's basically why it works fast. So I don't need to calculate the values of polynomials a and b in this point xi. I need to calculate powers of this xi. Yeah. And what's interesting about here? So all the powers of these x's will be inside the same set of values. Yeah. So if you take, let's say, x squared, and that's the second x, it will be this, and calculate it square, it will be this integer. So again, if you calculate, let's say, you want to calculate x2 squared, yeah. So it will be our power 2, it will be just our power 4. So again, all the powers of these x's will be in the same set of elements. So that's why it works fast, actually. Whew. Let's go. Now, let's calculate this. So I'll calculate this part. I will take elements, coefficients a of polynomial a, and calculate the values. ID. Let's put it here. So the algorithm, my algorithm will take some polynomial a. A0 plus a1 x plus and so on plus an minus 1 x and minus 1. And we'll calculate the values ui such that ui equals to value of polynomial a in point 12. So my algorithm takes n numbers, like coefficients of this polynomial, and returns n numbers, like these values. X is the basic polynomial. Yeah. No, x is just a free variable, so I won't use x. I don't need this x. I don't need this x. I need only coefficients of this polynomial. So I take the array of coefficients and I return array of values. Yeah, of x. Once again, my algorithm take values a0, a1, and so on, an minus 1. And construct a list of values u0, u1, and so on, un minus 1. Yes. If you think about multiplying, if you think about multiplying integers, then you just construct polynomial from each integer, and your value of your integer will be the value of this polynomial for x equal to 10. Yeah, if you work with 10. Yeah. So if you want to multiply long integers, you may think about a long integer as a polynomial when your digits of your integer is the coefficients and x equals to 10. Yeah. That's why it's basically the same to calculate the product of polynomials and calculate product of integers. Yeah. Go. Now we will use divide and conquer technique again, but slightly different. I want to take my polynomial and divide it into two polynomials, but slightly different, like in Karatsuba. I will divide it into polynomials. In one polynomial, I take all the even coefficients. In another polynomial, all the odd coefficients. So I'll take polynomial a1 as a0 plus a2 x plus and so on plus a even, so it's n minus 2 x power n minus 2 over 2. And polynomial a2 will be the polynomial of even coefficients, of odd coefficients. So a1 plus a3x plus and so on plus a n minus 1 and minus again n minus 2. So again, I take all the even coefficients in one polynomial and all the odd coefficients in another polynomial, like this. Now, what can we say about the value of polynomial a? Value of polynomial a will be, so I need to calculate the value of polynomial a1, but instead of putting x, I need to put x squared in these positions. So it will be value of polynomial a1 in point x squared, right? Plus, so here I want to put x power 3 and so on. Yeah. So let's just put this x to the bracket. So it's x multiplied by a2 in point x squared, right? Again, if you calculate this, what you will have? You will have these coefficients with x in power 2, 4, and so on, and these coefficients with x in power 1, 3, and so on. Yeah. So you calculate 1 plus double the power of your x. Yeah. Clear enough? Just say everything is clear. Everything is clear. So I'm a little nervous when you're so quiet. Say something. Now, I want to use divide and conquer technique. So to calculate my polynomial a in these points, I need to calculate value of polynomial a1 and a2 in these points. So I want to split my problem into two problems. So again, my problem is to take coefficients of polynomial a and calculate these values. I want to split this problem into two problems, divide this problem into two problems. So I will divide the coefficients of my polynomial into two separate polynomials. Say something. Making me very nervous. So again, I will repeat until you say everything is clear. So let's say polynomial a, something like let's say 3 plus 4x plus 7x squared plus 5x. So I want to split it into polynomials. So I have the first polynomial is 3 plus 7x, and second polynomial is 4 plus 5x. Now, if I put x squared here, I will have 3 plus 7 multiplied by x squared. And if I put 6, I have 4 plus 5 multiplied by x squared. Now, if I calculate this for x squared and multiply by x, so a1 of x squared is just 3 plus 7x squared. a2 of x squared is just 4 plus 5x squared. Now I multiply it by x, so I have 4x plus 5x cubed. Now I take sum of these two polynomials and get my polynomial. No. Now, what's the problem? I want to divide my problems into two problems. I already divided the coefficients into two polynomials, but I still need to calculate n values. So for these polynomials a1 and a2, I still need to calculate these n values. So I divided the number of coefficients by 2, but I didn't divide the number of values I need to calculate by 2. And to make a proper divide and conquer, I need to divide both these arrays by 2. So again, right now, what we did, we divided two polynomial into two polynomials of half size. But now for these two polynomials, we need to calculate the values for these n points. That's not good. I want to calculate values for only n over 2 points. But let's see. I need to calculate values a1 and a2 only in squares. So I need to calculate for each x again. I need to calculate values of this polynomial, let's say polynomial a1, only in point xi squared. So I need to calculate values of these polynomials only in points which are squares of my x's. Now let's see how many different squares are if you take these numbers as your x's. Well, let's look at here. So these are my coordinates. If I take square of these coordinates, which numbers I have? Now, let's draw another picture. I'll draw another picture here. So this is my W. So these are all powers of my W. Now, if I calculate the square of W, so I will have, so this is W, so this is, let's use this. So this number is W squared, right? This number will be W to the power 4. This number will be W in power 6. And this number will be W power 8. And now when you continue, you have the same for integer or for numbers, So this number will be 2 in power of 8, and it will be 2 in W in power of 10, and the W and also W in power 12, and also W in power 14. 0. So again, I need to calculate the values of these two polynomials in n points but in this n points, I only have 4 different values, n over 2 different values. Yeah? So I need to calculate values of polynomials a1 and a2 only in n over 2 points. Okay. So I will call it recursively the same function. I will calculate values. I need more letters. U. I don't have values u1 and u2. Okay, let's have values u1. So u1 it will be now. Okay, let's use more letters. We have the whole alphabet, right? So let's use letters. K. Why not? So let's say ki is the value of polynomial a in point xi squared. Yeah. Again, here I have only n over 2 possible values. So I will calculate these values only for n over 2 coordinates. So I'll recursively call the same function. So I will give this function coefficients a2, a4, and so on, and it will produce me the list of this case. Okay, n minus 1, k1 and so on, k n over 2 and so on. Again, why we need to calculate only n over 2 values? We need to calculate n values, but these values will be the same. So I need to calculate the values of polynomial a1 in these 8 points. But from these 8 points, there are only 4 different points, because w in power 2 will be the same as w in power 10, and so on. Oh, yeah, let's write it like this. If you take number w in power n over 2 plus 1, or plus I, let's say plus I square, it will be w power n, yeah, plus 2i. W in power n is 1, so it is the same as w in power 2i. So w in power n over 2 plus 1 square is the same as w in power I square. So for all my, and these are the points where I need to calculate my polynomials. So from these n points, there are only n over 2 different points. So I will calculate the value of this polynomial in this n over 2 points. And now I have proper divide and conquer. Yeah? So now I divided my problem into 2 problems of size n over 2. So for both these problems, I take n coefficients and I calculate the value of polynomial in n points. Ta-da! That's all. Let's write the code actually. Let's write the code. Yeah, takes enough. Let's have FFT of, let's give it my array A. let's give it n and this. Yeah. So again, this is recursive procedure. It takes coefficients of polynomial of size n and returns the values of this polynomial in this point. Well, let's say, so if n equals to 1, what you do when n equals to 1? If I have polynomial of size 1, polynomial of size 1 is a very simple thing. Yeah, polynomial of size 1 is just this single coefficient. So what is the value of this polynomial? Actually, value is the same for every point. Yeah, so it's just polynomial of size 1 is just a constant. So if n equals to 1, then we just return the single value, which is the value of polynomial n. Now, if n is not 1, then I will split polynomial into two polynomials. So we'll have polynomial I use big A and small a. Okay, let's use small a just for everything. So polynomial a1 will be a polynomial of coefficients a0, a2, 2, and so on. And polynomial a2 will be polynomial of coefficients a1, a3, and so on. Now I will recursively calculate the values of this polynomial in n over 2 points. So I will call k. Okay, why not k? K is so k will be the result of FFT polynomial a1 in n over 2 points with base w squared. And I need another letter. Smart. Like this. So k is the value is array of values of polynomial a1, and okay, let's see k1 and k2, and k2 is the array of polynomials a2 and n over 2 values. And now, just using these two arrays of values, I will find the values of my polynomial. Let's say okay, so it's array of size n. So how to find the value of polynomial a? I need to take value of polynomial a1 and value of polynomial a2. The value of polynomial a1 is in array k1. So the result for point I will be the value of polynomial a1 which is k1 in position I modulo n over 2. Plus w multiply w power I. Yeah? So this is my x multiplied by value of polynomial k2 in position I modulo n over 2. That's all. That's basically the whole Fast Fourier transformation. Once again, let's do it once again. let's have polynomial of, let's say, 8 coefficients. So you have 8 coefficients. You have A0, A1, A2, A3, A4, A5, A6, and A7. I want to calculate the values of this polynomial in some 8 points. So I want to calculate polynomial A in point W, polynomial A in point W power 0, W power 1, power 2, and so on, A in power 8. Okay. To calculate this value, I need to know the values of polynomial A1 and A2 in this point. So I need to find polynomial A1 in point W power 0 squared, power 0, A1 in point W 2, A1 in point W power 4, and so on. But again, if you look at the powers of W, then first 4 powers will be the same as the second 4 powers. Put all 8 variables. So, 4. I don't like it. Again, I want to calculate polynomial A1 in points W is power 0, W power 2, W power 4, W power 6, W power 8, 10, W power 12, and W power 14. Yep. So I need to calculate, again, I need to calculate values of polynomial A1 in this, for these powers. Right? No, that's strange. No, that's right. Yeah. So again, so this is xi squared, right? So I need to calculate values of polynomial A1 in point x squared. So these are all squares of my x's. In this array, there are only 4 different values. So these values are the same as these values. Because W power 8 is the same as W in power 0. Yeah. Again, n is 8, so W in power 8 is 0. Well, no, that is 1. W in power 8 is 1. 1 is W power 0. And this is the same as W in power 2. The same W power 4. It's the same W power 6. So to calculate my values, I need to calculate these values. But in these values, I only need to calculate this part. This part will be the same. So I run the same recursive procedure, give it only half of my coefficients, and ask to calculate only half of my values. So both these recursive calls take n over 2 coefficients and return n over 2 values. And here, this k1 and k2 returns a value of polynomial a1 in these points. And I want to have calculate in all these points. To calculate all these points, I take I modulo n over 2. So for small I will take this one. For big I will take this one. Makes sense? Say something. Why will work if n is not power of 2? Because I need exactly to split it in half. So here I kind of need that I have here because of this element. So what I use here? Here I use the w in power n over 2 square is 1. So if n is an odd number, I cannot do this. So I can do this only if n is an even number. So I want in all steps of my recursion, I want n to be an even number. If n is odd, yeah, I cannot do it like this. Yes, and to have n, if n is even in all steps of my recursion, I need it to be power of 2 in the very beginning, right? So I always divide by 2, and I must always have n as an even number. So it only works when n was a power of 2 in the very beginning. Well, actually, you can improve it if n is power of 3, for example. So if n is power of 3, you can divide it in 3 parts. If n is divisible by 3, you can do the same trick, but divide not in 2 parts, but in 3 parts, for example. So it's not only working for powers of 2, but for some integers which are product of some small prime numbers, let's say. Well, if n is prime, for example, it doesn't work at all. Yeah. So if n is a big prime, you cannot split it like this. So you will not find good power which has square equal to 1. Okay, that's all. So that's how you calculate these elements in n log n time. Yes, again, time complexity will be n log n. I skipped, but it's pretty obvious. So again, time complexity for n will be n plus twice place to n squared. So n will be n log n. Yeah. Why is it doing multiply? We need to multiply it by x here x. And for I, for this element, x is w in power I. Yeah, makes sense. Okay. Now we calculate these values of polynomial a and b. Now we calculate values of polynomial c. Now from these values we need to reconstruct the polynomial c. How to reconstruct the polynomial c? You make the inverse Fourier transformation. You basically do the same thing. Let's say that the I is the value of polynomial c in point w in power of I. Then I claim that the coefficients of polynomial c are calculated pretty simple. So coefficients of polynomial c, let's see Cj, and ci, we'll see ci. Coefficients of polynomial c can be calculated like this, as 1 over n by the sum of zj in power w in power I power j, like this. Yeah. Minus. I'll just prove it. I'll prove it in a second. So again, when I calculate values of polynomial c, I want to reconstruct the coefficients of polynomial c. I claim it can be done this way. So if you have these values of polynomial c, you can reconstruct it like this. How to do it? No, you're using the same thing. So this formula is basically the same as when you calculate the values of polynomial. So if you look at the these values as coefficients of some polynomial, then what you want to calculate here, again, you want to calculate values of your polynomial. And you can do it using the same algorithm as before. So we just do all the same thing to calculate these values. And then in the end, we will divide it by n and have the coefficients of c. Why is this true? No, let's see. I will just prove it. Again, there's unique polynomial with these values. So if I prove that the values of polynomial with these coefficients equals to z, then it proves that I have the correct polynomial. No, let's go. So let's try to calculate value of polynomial c in point w power I. What it will be? It will be the sum of all coefficients c j by w power I power j, right? Now, let's put these values here. What we'll have? We'll have 1 over n by sum. I need another variable. So I need to have sum of, let's say, k. So it will be zk multiplied by w power minus I, it's I, it's not I, it's j, minus jk. Yeah. Okay, this is j, so okay, let's write this. So let's be here, it's j, it's k. Yeah. Just to have the same variables. So I just take this coefficient and replace it with this formula and multiply it by w power ij. Now, let's look at this thing. So this thing is w. Let's rewrite it. So this thing is w in power. Let's put j versus I minus k by j, like this. Now let's swap the sums. 1n sum for all zk, okay, sum for all j, w in power I minus k power j. That's all. Let's write it like this. That's all. Now let's look at this formula. So again, I just calculated the value of polynomial c in some point, and this is the value. Now what do we see? So this thing is the sum of geometrical progression. So this thing is sum of geometrical progression. I have sum of something in power j. So what is the sum of geometrical progression? Sum of geometrical progression is w. Okay, let's use black. So what is the sum of geometrical progression? Is w power I minus k by n minus 1 divided by w I minus k minus 1. Right? That's how we calculate geometrical progressions. Yeah. So again, this you have some value. You take it in power of n, the size of your progression. Yeah, minus 1 divided by this number. Yeah. And now I claim that this number is actually 0, because what we have here? We have w in power of n. W in power of n is 0, where is 1? 1. W in power of n is 1. So we subtract 1 from 1 and have 0. So this sum is actually 0. Where's the trick? I have a 0 polynomial. It doesn't make sense, right? What do we miss? Yeah, just put it here. So w in power n equals to 1. So here I have something power of n. It must be 1. So I have 1 minus 1. It is 0. What is the trick? Q less than 1. What is Q? You mean this value? Yeah. The problem is when you have this number equals to 1. So if you have geometrical progression, if the this number in your progression is, how it's called, I don't know. So it's 1, so you have not increasing progression, not decreasing progression. You have a constant progression. So if this number is 1, you cannot calculate progression like this. You will have 0 divided by 0. So it's only 0 if I is not equal to k. So if I is not equal to k, and then I have non-zero, not 1. Here is not 1, something, doesn't matter what. What's only important is not 1. Something logic, so it will be 0. And if I equals to k, then I have 1, so this sum will be equal to n. So this sum equals to 0 for all pairs when I is not equal to k, and equals to n if I equals to k. Okay, let's put it to the end. So yeah, in the end, you will have, we'll move it here. So in the end, we'll have all elements of this sum removed, except the elements when I equals to k. And when I equals to k, I have 1 over n. Again, I equals to k, so I have zi multiplied by this sum. And this sum is sum of n units. So I have n. So it's zi. So again, if I calculate the value of my polynomial in point xi, I will have values I. It means I have the polynomial which have the values I need here. And since they're only unique polynomials, so this is exactly the polynomial I want to find. That's all. So that's how inverse Fourier transformation works. So for inverse Fourier transformation, you need to calculate this formula again. Calculate like this. And you do it exactly the same way like you calculate this Fourier transformation. So you do all the same things, except here you have w in power minus 1. But everything else is the same. So basically here you just was power j disappeared. No, I just take this as a sum of geometrical progression. So j is here. So this whole sum is the sum of geometrical progression. And this sum is either 0 or n. Okay, let's put here. So this sum equals to 0 for I not equal to k, and equals to n for I equals to k. That's all. You can get the same result if you just if you know how to calculate Lagrange interpolation polynomial. So it will be the same. So if you just take these values, calculate Lagrange polynomial, you will have the same thing. Slightly more ugly, but same thing. That's all. That's all. That's how you multiply polynomials. Again, let's evaluate everything one more time. So we have two polynomials. We extend the size of polynomials to the nearest power of 2. Now we take x as w power 9. Now we calculate the values of polynomial a and b in these points using this algorithm. Now we calculate values of polynomial c in the same points just by multiplying these two values. And then we use inverse transformation like this to reconstruct the polynomial c from these values. So both these parts are actually the same. They both works in n log n time. That's all. Okay, let's rewrite it actually. You can rewrite it slightly less ugly like this. So you can do it. You can iterate up to n over 2 minus 1, and here you have I minus 1. And calculate res in position n over 2 plus 1 as k1 I minus w power I. Yeah, just the same thing, just a little bit less ugly. So it's called butterfly transformation. So it's very easy. So you basically take these two numbers and calculate these two numbers. It's done for today. What is this beginning? Again, if you're working in complex number, you just calculate it as e in power like this. So they just need like sinus and cosinus of this 2p over n. And if you're working in prime modular, you need to find generator of this prime modular and put this generator in power p minus 1 over n. How to get generator we discussed in the previous lecture. So again, first of all you need to find a good prime model. You need to find prime model such that p minus 1 is divisible by b power 2, and then you need to find generator using this modular, like we discussed. Again, usually it's simple because again, to find the generator you need to factorize p minus 1, but we know that p minus 1 has many powers of 2 in it, so it's usually easy to factorize p minus 1. So again, you calculate p minus 1, factorize it. Then to find generator, you just pick random numbers and check if this number is generated. And then you find the generator, put it in power p minus 1 over n, and you have your number w. That's how you do it. Yes, easiest way to find generator is just to pick random number and check if this number is generated. Yeah. Good. Okay, I think it's good enough for today, okay?